Hello and welcome back to Unbounded Operators, the video series where we extend our functional analysis knowledge to operators that can have an infinite operator norm. And indeed, in today's part 14, we will talk more about unbounded self-adjoint and unbounded essentially self-adjoint operators. And there please recall that self-adjointness is something we already have for bounded operators, but the term essentially self-adjoint only occurs for unbounded operators. However, before I go into the definitions again, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that you can use the link in the description to download the additional material for the videos. And then without further ado, let's immediately discuss the definitions again that work in a Hilbert space X. This means the operators we consider here map X into X itself. So we just have a linear operator T that could be unbounded. And this also means that we have a domain of definition given, which is in general smaller than the whole space X. However, we usually assume that the domain is dense in the space X. This is helpful because a densely defined operator has a well-defined adjoint that we call T star. And by definition, this new operator also has a domain of definition in X. And as always, this thing is crucial because we would say that T is self-adjoint if it coincides with its adjoint in the operation and also in the domain. So there we have our first important term. Self-adjointness makes sense for a linear operator from X to X. And then the definition just consists of two parts. First, we need that T is densely defined, because otherwise the adjoint would not exist, and on the other hand, T star should be equal to T. And when we write the equality sign here, this also includes that the domains coincide. And at this point we can also recall that if the domain of the adjoint gets larger, so it's a superset of dt, then we would say that we have a symmetric operator. In other words, a self-adjoint operator is a very special case of a symmetric operator. And in fact, it's a very important case because, as we will see later, for self-adjoint operators we have the spectral theorem. Therefore, our goal is often to reach a self-adjoint operator, and sometimes this is not so complicated. Namely, this is the case when we have a so-called essentially self-adjoint operator. And as the name suggests, it simply means that we can easily extend T to a self-adjoint operator. And we can do that by simply forming the closure of T. Therefore, here we have to assume that our densely defined operator is also a closable one. And as always, closable just means that we can find an extension of T that is closed. And now it turns out that this property is necessary to find a self-adjoint extension as well. Simply because every self-adjoint operator is also a closed operator. This fact is really easy to show and definitely something you should remember for the rest of this series. So the statement here is simply, if we have a self-adjoint operator, it implies it's also a closed operator. This means the best case for a non-closed operator would be to be essentially self-adjoint. Okay, then let's quickly prove this implication. We just have to put two things together, and the first part is from part 13. There we have already shown that a symmetric operator T is necessarily closable. So we can also use this fact for self-adjoint operators. And on the other hand, we can also use part 11, which tells us that the closure of an operator is given by the double adjoint. More precisely, what we put in now is that we have a densely defined operator which is also closable. And in that case, the double adjoint of T is well defined and given by the closure of T. And now we can simply use both facts for a self-adjoint operator. And this immediately tells us that we have a densely defined operator which is also closable. This means we are allowed to use this implication here from part 11. And moreover, we can also use our self-adjointness to reformulate this double adjoint. And by definition, it's just the adjoint of T star. However, by the self-adjointness, T star here in the middle is just given by t itself. Which means we just have this outer star here, so t star again. And then in the last step we can just use the self-adjointness again and we get t on the right hand side. So the conclusion of that is that the closure of t is just t itself, which means t is already a closed operator. So you see, this was not much work, but it's definitely a property of self-adjoint operators you should remember. So again, a non-closed operator can never be self-adjoint, but the best thing we could have is being essentially self-adjoint. So you have to form the closure and check for self-adjointness there. And there you might find that it is easier to form adjoints, so instead of the closure of t, you can also look at the double adjoint. Indeed, this is one possibility, and it might be helpful to put all the possibilities in one proposition. So let's say that we have a Hilbert space given, and that we already know that t is a symmetric operator. So in particular, by definition, it has to be densely defined, and we already know it's a closable operator. So in particular, the strategy to get the closure of t with the double adjoint definitely works. And now it turns out that we can even formulate more equivalent terms. And all are equivalent to the best case we can have, which means that t is essentially self-adjoint. Hence the second statement here is, as already mentioned, that the double adjoint is a self-adjoint operator. However, now it turns out that we don't have to form the adjoint twice, because it's good enough to look at the adjoint of t itself. This one is already self-adjoint if t is symmetric and essentially self-adjoint. And in fact, we can put this even into a weaker form and say that t star is only symmetric. And that's it. And now we just have to show that all these four statements here are actually equivalent. So we have a few implications to show, but some of them are already quite trivial. For example, we already know that 1 and 2 have to be equivalent. Again, this just follows from the fact that the double adjoint is just the closure of t. Hence, this also implies that the adjoint of both operators coincide. So in a formula, we just have that the closure of t with a star is equal to t with 3 stars. And now you should see that the equality here on the lower part is just the statement in 1. And on the other hand, the equality in the upper part just means that t star star is a self-adjoint operator. And there you see it, one equality holds if and only if the other one holds. And this is really good because it means only 4 implications remain to show. And moreover, 2 are already given because self-adjointness implies symmetry. And on the other hand, if something is self-adjoint, we can use the star operation as much as we want without changing anything. This means we don't have to write down anything for 3 implies 4 and 3 implies 2. So the actual work here is to show the converse, and let's start with the implication from 2 to 3. This means we now just assume that the double adjoint is self-adjoint. In other words, putting the star to the double adjoint does not change anything. However, obviously, we can see t star star as the adjoint of the adjoint. This is quite clear, but it helps us because now we have an equality for adjoints. To make this clear, we could call the double adjoint of t just u and the adjoint of t v. And these are well-defined operators on the Hilbert space X, and they are also closed operators. For that, please recall that the adjoint of a densely defined operator is always a closed operator. So again, what we actually have here is an operator equation, u star is equal to v star. So it's not a problem at all to use the adjoint operation on both sides again. And there we can just use that the double adjoint is always equal to the closure of the operator. However, since the operators are already closed, we don't need to use the closure at all. The closure is already equal to the operator itself. So what we get from this calculation is that the operator u is actually equal to the operator v. And by substituting the names again, we just get that t star star is equal to t star. And with that we are done, because this equation tells us that forming the adjoint of t star does not change the operator at all. In fact, this one is exactly the definition of T star being self-adjoint. And with that, the implication 2 going to 3 is done. And then you see only one implication remains to show, namely the one that T star symmetric already implies that T star is self-adjoint. So there in the assumption we have two symmetric operators, T and T star. And there you just need to know that symmetric means that the adjoint is an extension of the original operator. So the domain of the adjoint of T star does not get smaller. And here please don't forget, this is just the double adjoint on the right, which is given as the closure of T as always. So by assumption, the closure of T is an extension of T star. And similarly to before, we can use that both operators are closed operators. And we can combine that with the fact that T itself is also a symmetric operator. And by definition, this means that T star is an extension of T. Hence what we get here are two extensions of our original operator T. Both are closed operators and we know this is possible. But most importantly, you should know that the closure is always the smallest possible closed extension of an operator. Hence we immediately get that T star has to be equal to T bar. And this equality is all we need to show the self-adjointness, because we already know that the closure is always given by the double adjoint. So you see the adjoint operation does not change our operator, and this is what we call self-adjoint. And this is what we wanted to show. This justifies the last implication. So the whole proposition is just proven now. And what you can take from this proposition is quite important, because it tells us that we only need a symmetric operator where the adjoint is also symmetric to already have an essentially self-adjoint operator. Okay, so I think this is good enough for today, and in the next videos I will definitely show you more examples where we can see these nice properties of self-adjoint operators. So I really hope I meet you there again, and have a nice day. Bye bye.